Yeah, that's what I get practicing Turkish.
Okay, I think I can start. Well, thank you for everyone for coming here today to listen to my presentation. My name is Melih Kamaoğlu. I am PhD candidate at Bartlett School of Architecture, University College London. I am also visiting researcher in here for 3 months until December, and my supervisor is Philosophers. And today I'm going to give you a summary of my PhD research, what I have been up to. And the title of the presentation is The Idea of Evolution in Digital Architecture. And basically, I'm trying to understand how architects have used the idea of evolution in biology by using various computational design tools. So it is kind of historiography of the last 30 years, but also it is kind of critical review of it beyond just that historiography. So of course, if we're going to talk about the relationship between evolution, computation, and architecture, it is basically starts with this relationship between human and nature, because as you know, we always try to understand how nature works, and we try to reflect that knowledge in our design and practice. And we used to consider nature as a kind of sort of intelligence, sort of inspiration and creativity for architectural design procedures. In that way, actually, there is this comprehensive relationship between the philosophy of nature and architectural design. And what I mean by philosophy of nature is how we understand nature and then how we reflect that in the architectural design procedures. So if we look at the history very briefly, there is 3 conceptions of nature we can see in the literature. So nature as an organism, which was in ancient Greek, and nature as a measurable and quantitative fact, and nature as an evolutionary process. So my research is mostly about the last part, the nature as an evolutionary process. But let's have a look at for example, ancient Greek. As I said, in ancient Greek, there was this idea of nature as an organism, and there is this mind arranging the order in the universe. And if you look at some of the philosophy of natures back in that time, for example, theory of forms by Plato, how it was reflected in architectural design as a search for some ideal forms in architecture. Or Pythagoras, right? The idea that the essence of nature is geometry has been reflected in architectural design as a search for primary geometrical forms. Or think about Aristotle, the idea that there is this development towards purpose and completeness in nature, and it was reflected search for perfection in design. So at this stage, what you really need to understand is that in ancient Greek, we were trying to understand nature with our minds. So the only agency we have is looking at nature, making some ideal perspectives on nature, and trying to reflect it in architectural design. But if we move into Renaissance, we start to try to understand nature with the scientific models, which is measurable and the quantitative, of course. And if you think about it, in Renaissance, architecture was understood as the mathematics, as the science itself. And there was this search for idea of universal space, for example. Or think about it, there was this search for symmetry in architecture and the part-to-whole relationship. All is coming from how we understood nature in the Renaissance practice, I would say. So in the Renaissance, like I said, in ancient Greek, the only agency we had was our minds. But in the Renaissance, we started to make analogies with the machines. So there was this analogy between how machine works and how the living nature itself works. And as part of that analogy, I would say, that was reflected in, again, architectural design practice. So when we come to modern times, the idea of nature was mostly inspired by the evolutionary processes. Because when it comes to modern times, the evolution theory has become essential power of how we understand nature itself. So for that very reason, it is really important to understand the role of evolution theory in the history and also in the digital architecture. But this time, we are moving forward. We started with our minds, then we embraced the machines, but this time we have computers and also evolutionary perspective about the nature. And we started to use computation itself as part of the design procedures. So as I said, evolution theory is, I think, undeniably one of the exceptional scientific development we need to understand. Because before the evolution theory, there was this idea that nothing in nature changed. All the living organisms are perfect, and they have some degree of perfection in the ladder of being, as you can see in the screen, great chain of being. But when it comes to evolution theory, and especially after the Darwin, we started to understand nature as a changing, evolving, and responsive dynamic reality. So this is the quote from the last page of Darwin's book on the origin of species. I'm not going to read the whole of it, but the last part is really important. From so simple a beginning, endless forms, most beautiful and most wonderful have been and are being evolved. I think this is a huge paradigm change, and this paradigm change has been reflected in digital architecture in the last 30 years, and we will see it in a moment. Of course, evolution theory is not restricted to just Darwin. After Darwin, we started to understand all these processes from gene to environmental scale, actually to maybe planetary scale. And the impact of evolution theory is not restricted with biology, of course, because thanks to the developments in computer science, we started to represent computational equivalents of evolution. So with these computational tools, basically digital computation tools, we started to kind of simplify the complexity of life into some codes, to some computer codes, basically. But beyond digital computation, there was another emerging area which we call unconventional computing or non-classical computing. This has nothing to do with digital computation. This is directly using materials, whether living or non-living, itself as a sort of computation. But why we were interested in it, because this is computing with nature. This is directly using life itself as a sort of computation. So you can call it maybe physical computation. It is not binary. It is the interaction of material with the environment. So finally, after the beginning of 1990s, mostly, architects started to embrace these computation procedures to represent and to embed the complexity of life, all these processes you can think of in the design process. And after the 1990s, there was this generative and responsive understanding of form in architecture, and basically it is a bottom-up approach to design practice. And then we started to have this increasing power of computation, and thanks to that, we started to use this evolutionary logic of try and error for form-finding experiments in architecture. And as part of it, actually, the impact of the designer, authority of the designer, has started to be diminished because we are allowing another agency in the design process. And then towards, I would say after 2000 probably, 2010, architects also started to use these physical computation procedures. So the idea right now is both using digital simulation, digital computation to simulate something, but also using the living material itself and trying to find some intersections between digital and the physical. So this promoted the idea of biodigital design. I'm sure you heard it. And the question of biodigital fusion or unification. So this is what I am doing, basically. It is the historiography of last 30 years. So many architects I'm looking at, and I'm trying to understand how they understood evolution itself and what kind of computation procedures they used and for what purpose they used it. Like I said, many architects, and beyond the publications of these architects, I also do interviews with them as part of my PhD research, so as a kind of extra information. So all these architects have different connections with different evolutionary concepts. So in the end, all the thing in my doctoral research is figuring out this relationship between these 4 boxes you see in the screen. Like, first of all, there is evolution as it is in nature, and there are some evolutionary theories and philosophies trying to explain some of them on some scales, and there are some computation procedures we are using to embed evolution, and there is digital architecture. For that reason, in order to understand this relationship, we need to ask questions like, what kind of evolutionary process we are talking about? In which scale? Like, there are many scales in nature. And if the architect is referring to some scientific theories, then we need to ask what kind of scientific model. Is it neo-Darwinism? Is it in the symbiosis theory? So all have different implications for design procedures. And in the next step, you need to ask, like, what kind of computation procedures? Are you going to use just AI to simulate some behavior in nature? Are you going to use some genetic algorithm just to explore variety of your forms? So which one it is? And the last part, of course, why architects are bothered to use this? Like, why using evolution as a kind of design methodology? It is an important question to ask. You can just use it for optimizing your form. You can use it for aesthetic purposes. Like, it's up to the architect. Of course, it is not possible to go through like every architect and what they said. For that reason, I will just show you 5 examples from the literature, and I believe these 5 examples will show you a variety of work regarding how they understood evolution and what kind of computation procedures they used and what kind of biodigital design theory they proposed. So the first one I would like to show you is, before I move on, just forget about the names, please. I mean, it is not important, the names of these architects, but the idea is much more important. So the first one is John Fraser and his book in Evolutionary Architecture, which was published back in 1995. And in here, what we see, students in the studio were using neo-Darwinian theory, like creating mutations, variations of the form using genetic algorithms, and they basically used cellular automata as a kind of design model. But for what purpose? Just to experience and experiment with the form-finding experiments. For example, you can see one of the examples in the screen. It is starting from very simple complexity, but in the end, it is evolving into much more higher complexity, I would say. But of course, in order to have this design logic, first you need to define your design concept as a kind of generative rules, because you are not designing the output, you are designing the rules itself. And in the next step, your generative rules should correspond to some form generation processes. And then you need to test it against some fitness criteria. You need to have a fitness criteria to eliminate all these variations emerging in your screen, I would say. And if you think about it, these forms, these emerging forms are actually unpredictable because there is element of randomness in this process because you are allowing genetic algorithms to do some job in the process. So you're not designing final output, you're designing rules, and you're designing actually the possibility space for your architectural form. And before we move on, another thing to note in here, let's say I just want to take one of the forms in the screen and I just want to build it. So right now it's just a geometry, but we don't know how we can build it in the real world. And the expectation is not that once I build it, it's going to continue to evolve. So all the evolution I'm referring in here is just about virtual environment. It's inside the computer. So all these emerging forms doesn't have any materiality. So it is just emerging geometries, playing with the geometry itself. Another example is Greg Green, I'm sure you know him, and his ideas back in 1990s about animating form and his biological houses project. So in here, actually it is quite similar what I showed you with John Fraser, but in this one, the reference is not to neo-Darwinism. In this one, the reference is in the symbiosis theory in biology. So, and if you read his writings, you will see that he's kind of against neo-Darwinian logic in the design process. He is criticizing neo-Darwinian perspective for form finding because, like I said, there is random mutations, there are some external selection criteria, so he's kind of critical. And in here, I think what is really interesting is understanding form itself as a kind of, formal geometry is a kind of evolutionary space. And in this evolutionary space, there is iterative, continuous transformation of the form, I would say. And another interesting idea in here is promoting the idea of evolution just for endless variations of the form, to see the variety of the forms emerging, I would say. So to do that, of course, you need to first set up some parameters and you need to play with the geometry itself, with the control points. Then you transfer that geometry into smooth forms you see actually in the screen. And in here again, before we move on, again, there is no materiality. When it comes to building up this model, you need to think about it. So the evolutionary process inside of the computer doesn't have any materiality, and the expectation is not that it's going to evolve in the real nature. And now it's time for moving forward to another thing. It is morphogenetic design theory. Again, in here, the reference is to neo-Darwinism as a kind of design logic, but this time, in the evolution of the form, even though it is happening inside of the computer, we are starting to think about the materiality itself. How the material behavior we select for that form will affect the evolution of that form, even though it is inside of the computer. So the idea is using the material behavior and the performance capacity of material, kind of using it as a kind of selection criteria for that variations of the forms emerging. So for that reason, evolutionary process is not just used to generate variations of the geometry itself, but in here, both formal, structural, and the material qualities are considered together in the evolution of the form. And evolution of the form is not just dependent on that neo-Darwinian universal model, but in here, there is direct reference to physical world. But of course, I'm saying there is materiality in it, but it is still dependent on your simulation tools. So I'm not talking about actual physical behavior of that material, but simulation of it. And it is integrated again inside of the computer. So material itself is becoming some sort of co-designer in this one. But it is not the actual physical behavior. It is a simulation again. Moving forward, this time, in this one, in a couple of projects from Lab Studio, from Gen 7, what I see is all the things I mentioned, like digital simulation of nature, making reference to some scientific theories and so on, all is there. But this time, designers starting to look at how the structure itself can continue to evolve or respond to environment after we build it. So this is one step forward. Now the digital and the physical in terms of evolution is much more coming together. The gap starting to get much more closer, I would say. And in the book, when I was reading the book, I realized that there is this really exciting argument about design process, because they understood design as a kind of continuous evolutionary process of the forces, not the objects and their relations. So for that reason, what we can say, actually architectural design as a kind of object, as an output, is only secondary quality of evolutionary process. So we are not just thinking about how it will look like in the end, but we are looking at the process, and not just in the digital world, not just in the virtual world, but also physical world. For example, if you go to visit one of these structures, at least some of them, there is an interaction. It can respond to some climate, it can respond to you, to your movement. Of course, the idea is not like real, like evolution of organisms or something. This is not something living, but it is responding to environment. So the process is still considered after we build the structure. And I think it is really an important step. So the last one is Pisarium computation. I don't know if any of you heard it. I'm really wondering if anyone heard the Pisarium computation in here.
Yes.
Great. So this is kind of interesting one, and it has emerged in the last 10 years, I would say, in architecture discussion. And it was used by architects for urban design projects, for form finding experiments. So this is an actually slime mold, Pisarium polycephalum. This is a living organism. And what is really interesting with this organism is, at its plasmodium stage, it is starting foraging behavior, like you see on the screen on the right-hand side. It is foraging, and it is finding the food sources around and making some connections with that one, and creating some networks, as you can see in the screen. So what is different with Pisarium computation in terms of this topic is it is a computation, it is a computing with nature. So the idea is not just looking at this organism and trying to emulate its behavior with machine learning algorithm or any kind of algorithm, but the behavior of the organism itself is computation. And you're directly integrating it into your design project. So it is in here, all the evolutionary and the morphological processes, we understand it within the complex interaction of this I would say, living organism. And in the literature, if you look at the literature, you will see that Pisarium computation has been considered by scientists kind of one step forward in the physical computation, because it creates these dynamic networks with efficiency, with fault tolerance, comparing the real-time infrastructures and real-time, let's say, road networks. And of course, with digital computation, we are confined within the limits what digital computation can do, which is a mostly abstraction of the reality around us. But with this one, we are confined within the limits of the agents of this organism, right? Because it is making decisions itself. We do not have 100% control about how it's going to behave, what kind of form it will emerge, and so on. We can partly direct its behavior, but it is not 100%. And of course, maybe that's the beauty of it, because you're allowing another living organism kind of as a kind of co-designer in the process. But I really suspect that if this organism has any idea about design purposes, probably doesn't have any idea. It is just doing whatever it is doing, but it is becoming part of the design process. So, of course, wrapping it up, what is the conclusion in this presentation? I just wanted to show you that if you're thinking about the idea of evolution in digital architecture, it is starting with pure abstraction back in 1990s. Pure abstractions, pure analogies with some scientific models of evolution. And on the way, we started to embrace the materiality of the form in that evolution of the form. Then we started the materiality in the physical world. We started to think about the physical world. And at the last stage, as I showed you with the Pisarium, it is directly using nature itself as a sort of computation. And using both digital computation and the physical computation for architectural design purposes and trying to find some intersections in between. So the question in here is, can we call there is biodigital fusion or unity, or let's say there is a unification between physical and the digital in architecture? I really suspect that, because if you are dealing with the digital computation, in my opinion, you have to simplify things. If you are doing binary computation, you have to simplify. You cannot just run away from it. And I believe that in the last 30 years, this gap between physical and the digital is becoming more and more closer. I believe that. But I think there is some degree that we cannot go beyond because of the nature of the tools we are using. And I know that some people argue that, well, it is about the computing power. if you're going to have more computing power, maybe you will have a chance to simulate the whole complexity of life and so on. But I think if you are talking about binary computation, like the one coming from Alan Turing, I think that's the part of the nature. You cannot change it. But if you're going to have different kinds of computing in the future, that's another discussion. So before I finish my presentation, I published an article about this topic. Check it out, and if you have any interest in this topic, and let me know what you think about it. You can send me an email, and you can also contact me on social media. Thank you for listening.